Every conversation about running AI on your own hardware is a conversation about gigabytes. How many gigabytes is the model? How many gigabytes does your card have? Can you quantize it down a few gigabytes? The entire vocabulary of local AI is measured in the same unit as a video file. This one is 14 megabytes. Not 14 gigabytes. 14 megabytes. Smaller than a single high-resolution photograph. It runs an entire session in about 28 megabytes of memory, which is less than most browser tabs. There is no graphics card involved, there is no download of separate weight files, and the documentation describes it running on phones, on wearables, on smart home hardware, and on robots. And it currently has more than 8,000 stars on GitHub from a company with a real engine behind it and a paper behind that. Now, before anybody gets the wrong idea, because this is the part most coverage will skip, and it changes everything about whether this is useful to you. This is not a chatbot. 45 million parameters cannot hold a conversation, cannot write your essay, and cannot answer general questions about the world. If you install this expecting a tiny version of the assistance you're used to, you will be disappointed inside 30 seconds. And that disappointment would be entirely your setup and not the model's fault. What it does is narrower, and I'd argue more interesting. Tool calling, device use, and structured extraction. You give it a set of functions it's allowed to call, it decides which one your request means, and fills in the arguments correctly. Or you hand it messy text and a shape, and it returns that shape filled in. That's it. That's the whole job. And the argument this project is making is that that job is worth doing on the device, and it does not require a large model to do it well. 3 things today. First, what it actually is, and the 5 design decisions that make 14 megabytes possible, and one of them, the way memory is handled, is a genuinely clever answer to a problem that breaks most small models. Second, the architecture. Because the question everyone will ask is how you get useful behavior out of 45 million parameters at all. The paper's answer includes one idea I find delightful: a chunk of the model that does real work while containing no learned weights whatsoever. And third, the honest picture. What the benchmark claim actually says, what this can't do, and the 2-tier design pattern the same company is quietly building around it, which I think is where this whole category is heading. Standards note: everything comes from the project's own documentation and repository page. Read this morning, quoted verbatim where it matters. The benchmark comparison is theirs, and I'll say so again when we reach it. It's Apache licensed as of 4 days ago. Let's go. What it is and the 5 decisions. Start with the shape, verbatim from the README. Needle 2 is an open 45 million parameter model for tool calling, device use, and structured extraction. The whole model is a single 14 megabyte binary that runs a full session in about 28 megabytes of RAM. Every clause there is load-bearing. Let's take the 5 properties they list, because each one solves a specific problem that would otherwise make a model this small useless in practice. 1. Self-contained. The weights are baked into the engine. There is no model file sitting next to a runtime. The 14 megabytes is the whole thing. And then a phrase I want to underline verbatim: inference does no network. That's not a privacy slogan, it's an architectural fact with consequences. It means this works in a basement, on a plane, in a factory, on a device that has never had an internet connection. The documentation even covers offline setup for air-gapped machines, for anything embedded in physical hardware. Does no network is not a feature, it's the entry requirement. 2. A simple contract. Text goes in, structured data comes out, and the mechanism, verbatim, a byte-level grammar compiled from your schemas, constrains every token. This is the most important sentence in the entire README, and it deserves unpacking, because it explains how something this small can be trusted at all. Normally, when you ask a model for JSON, you ask nicely and hope. The model produces text. That text is usually valid JSON, and sometimes it isn't. A missing brace, an invented field, a number where a string should be. Every developer who has parsed model output has written the retry loop for this. Grammar-constrained decoding removes that possibility entirely. At every single token, the decoder is restricted to only those characters that could legally continue a valid structure according to your schema. Not, the model tries to produce valid JSON. The model is incapable of producing anything else. Malformed output isn't unlikely, it's unreachable. And that is precisely why a 45 million parameter model can be useful here. A big model spends part of its capacity learning to be well-formed. This one doesn't have to, because well-formedness is enforced outside the weights. The grammar does the work the parameters would otherwise have to do. 3. Confidence-gated. Verbatim, every response carries a calibrated confidence score from a learned head. Set a threshold, act above it, escalate below it. Think about what that buys you on a device. A small model will sometimes be wrong. That's a certainty, not a risk. The question is what happens next. Without a confidence signal, wrong answers and right answers look identical, and your application has to treat every response as equally trustworthy. With one, you can write a rule. Above this threshold, act on it locally. Below it, send this one somewhere bigger. A model that knows when it's unsure is worth considerably more than a model that's slightly more accurate and can't tell. We'll come back to that because the same company has built a whole repository around it. 4. Tool retrieval. You can declare a large catalog of tools, and a built-in retrieval head renders only the top 5 tools per turn, with the grammar constrained to that subset. That solves the obvious scaling problem. If your smart home system has 200 functions, you cannot put 200 schemas into a 256 token window. So the model first narrows to 5 candidates, and then the grammar is constrained to just those retrieval and generation in one pass inside 14 megabytes. 5. And this is the clever one. Bounded memory. Verbatim, a 256 token sliding window with the tools pinned as KV sinks. So total memory stays near 28 megabytes no matter how long the conversation runs. Here's why that matters more than it sounds. In a normal model, the memory needed to hold a conversation grows with the conversation. Every exchange adds to what has to be kept in memory. On a big machine, that's a cost. On a wearable with a fixed memory budget, it's a crash. A device that works fine for 10 minutes and then dies is worse than one that never worked. So they made the window fixed and small. Old content slides out, but the tool definitions get pinned in place. They're the one thing that must never fall out of the window, because losing them means the model forgets what it's allowed to do. So they're anchored while everything else scrolls past. The result? Memory usage that is flat forever. 28 megabytes at the first exchange and 28 megabytes at the 1000th. For anything shipping in a physical product, that predictability is worth more than raw capability, because you can size the hardware once and know it will never be exceeded. The architecture and the part with no weights. Now the question everyone asks, how do you get useful behavior from 45 million parameters? The README calls the recipe a simple attention network, and the ingredient list verbatim is a Hadamard MLP in place of the feed-forward network, grouped query attention, engram key-value memory, and multi-lane hyperconnections. There's a full paper with the design and its ablations. I'm not going to pretend to have read that paper end to end, and I'm not going to fake depth I don't have, but the README states the crucial property outright, and it's the bit worth understanding. In a standard model, the feed-forward block is where most of the parameters live. It's a large learned matrix, and running it means reading every one of those weights out of memory for every token, which, as anyone who has watched a local model generate slowly knows, is the actual bottleneck. The substitution here is a Walsh-Hadamard Transform, and the README describes it with the phrase that made me stop. A fixed matrix applied in n-log-n time with no weights to read. Sit with that. A Hadamard transform is a structured mathematical operation made entirely of +1s and -1s in a fixed pattern. It mixes information across a vector thoroughly, and it does so with a fast algorithm, the same family of trick as a fast Fourier transform. It's not learned, it's not stored. There is nothing to load, it's an operation, not a table. So a chunk of what a normal model does with hundreds of millions of learned parameters, this does with a mathematical identity that costs 0 bytes on disk and 0 bytes in memory. That is the single clearest answer to, how is it 14 megabytes? Some of the model isn't stored at all, it's computed, and you only need learned weights for the parts where the specific values genuinely matter. The other pieces follow the same instinct. Grouped query attention shares key and value projections across query heads, a standard technique now, and the reason the memory story works at all. N-gram key-value memory gathers rows from hashed n-gram tables, which is a lookup rather than a big matrix multiply. And routing is normalized with a technique from optimal transport to keep the assignment balanced. Then the whole thing is compressed to roughly 2 bits per weight with the company's own quantization method and baked into the engine, which is how the arithmetic closes. 45 million parameters at about 2 bits each is roughly 11 megabytes, plus the engine, and you land at 14. The parameters got fewer, the ones that remain got smaller, and some of the work moved out of the weights entirely. 3 multiplications, and the product is a model that fits in a photograph. What runs on your phone actually means. Worth being concrete, because runs on a phone is a claim people have made loosely for 2 years, and it usually means runs on a flagship phone for a while until it gets hot. This is a different scale of claim. The repository's own description names the targets: phones, wearables, smart home, and robots. Not phones as the small end of the range, phones as the large end. Put 28 megabytes in context. A modern phone has somewhere between 6 and 16 gigabytes of memory. This model's entire working footprint is roughly 0.2% of the smaller of those. It isn't competing for memory with your other applications, it's a rounding error inside one of them. And that changes what's possible architecturally. A model that needs 2 gigabytes can exist on a phone, but it can only exist as the application. You load it, you use it, you close it, and the operating system reclaims it the moment you switch away. A model that needs 28 megabytes can be resident. It can sit inside your app permanently, ready with no load time and no eviction, the way a spell checker does. Those are completely different products, and the difference is entirely a memory figure. Then go a tier down. a smartwatch, a thermostat, a set of headphones, a sensor on a factory floor. These have memory budgets measured in tens or low hundreds of megabytes and no accelerator whatsoever. That tier has never had a language model of any kind, not because nobody wanted one, but because nothing fit. The smallest useful thing was still an order of magnitude too big. And the compounding property here is the bounded window. On a device with a hard memory ceiling, a model whose memory grows with conversation length isn't merely inefficient, it's unshippable, because you cannot certify hardware against a number that keeps rising. Flat memory is what makes it a component you can design a product around rather than a demo you run once. Reading the benchmark claim honestly. Their comparison verbatim, it trades wins with other small models like Function Gemma 270 million, LFM 2.5 230 million, and Apple's Foundation model at 5 times to 70 times smaller and 2 bits against their 16-bit. Take that phrasing seriously, because they chose it carefully. Trades wins is not beats. It means on some tasks this is ahead and on others it isn't. That is a considerably more honest framing than most launch material, and it's the right way to describe a scatter of results. The claim that carries the weight is the ratio. Roughly comparable performance against models 5 to 70 times larger, and at 2 bits per weight against their full precision. The headline isn't that it's the best. The headline is that it's competitive at a size where competitiveness wasn't supposed to be available. And a caveat I have to state, these are the project's own published comparisons against models they selected on a benchmark suite they chose, and I have reproduced none of it. Their peer group is also the right peer group, small on-device tool calling models, which means this tells you nothing about how it compares to anything you'd normally call an AI assistant. Different category entirely. Using it, and the line that decides your results. The practical part, and it's short because the design is genuinely simple. Install the Python package. Then you decorate an ordinary function with a marker, and the README explains what happens next. The signature gives the argument types, the docstring is the tool description. That's the whole integration. Your existing type hints become the schema, your existing docstring becomes the description. There is no separate schema file, no registration ceremony, no configuration. You hand the model a list of your functions and call run, and it picks the call, executes your function, feeds the result back, and returns the answer with the executed results attached. For extraction, it's the same shape. Declare a data class describing what you want pulled out of some text. Call extract and get back a typed object with the fields filled in. Structured data out of unstructured text, locally, in 14 megabytes. And then the sentence I'd put on a poster if I ran this project, verbatim. Needle reads your tool descriptions to decide what to call and how to fill arguments. So describing them well is the whole game. That is the honest instruction manual for the entire category. A small model has no general world knowledge to fall back on. It cannot infer that your function called procdate handles dates because it has seen a million codebases. Everything it knows about your tools is what you wrote in the docstring. So a vague description is not a small problem, it's the whole problem. With a large model, sloppy descriptions cost you a little accuracy. Here, they cost you everything. There's also a local browser playground, one command, and you get an interface where you can edit tools and prompts and run them, with follow-up queries continuing the same conversation. And a nice touch in the docs, the server downloads and initializes the model before it starts serving. So your first query is instant rather than hanging while something loads. And fine-tuning is where this gets genuinely practical. It uses low-rank adaptation on a frozen base and merges the adapter at export, so the result is a single portable file. Training is plain JAX and runs on whatever accelerator you have. There are install options for NVIDIA hardware and for Apple Silicon. You can optionally synthesize training data from your tool schemas using an external gateway, though that's the one step that requires an outside service. And the detail that makes the whole loop work verbatim. The engine is weights agnostic, so a tuned CACT runs on it directly, no recompilation. Tune it for your specific tools, export one file, drop it on the device, done, no rebuild, no toolchain, no native compilation step. For anyone who has shipped machine learning to embedded hardware, that sentence is the difference between a weekend and a quarter. Who's behind it and the pattern they're building. Worth a beat because it reframes the model as part of something larger. This comes from a small British company, and the model is not their only repository. There's a separate project, quantization, kernels, runtime, and inference engine for mobiles, wearables, smart home, and robots, written in C++, with nearly 6,000 stars of its own. So the engine underneath this has an independent life and an independent audience. And then there's a third repository, and its one-line description is the most interesting sentence on their entire organization page. On-device models that know when they're wrong. Every answer carries a confidence score for cloud handoff. That is the thesis. Not small models will replace large ones. That claim would be silly, and they haven't made it. Instead, run the small model locally, have it grade its own certainty, and escalate only the cases it isn't sure about. Think about what that architecture does to a product. The overwhelming majority of requests to a device assistant are routine. Turn this on, set that, extract these fields. A 45 megabyte footprint model handles those instantly offline, with no per request cost and nothing leaving the device. The genuinely hard ones get forwarded to something large. You get local speed and privacy for the common case and frontier capability for the rare one, and the confidence head is what routes between them. That's not a compromise between local and cloud. It's a design that uses each where it's actually better. And the economics of it are worth stating plainly, because they're the reason this pattern will spread whether or not this particular model wins. Every request a device handles locally is a request that costs nothing per call, adds no latency, needs no connection, and sends no data anywhere. Every request escalated to a large model costs money, adds a round trip, and requires both a network and a decision about what leaves the device. So the value of a confidence score is not academic. It's the dial that sets what fraction of your traffic is free. A model that knows when it's unsure lets you push that dial as far as it will safely go. A model that doesn't forces you to either escalate everything, which defeats the point, or escalate nothing, which means shipping wrong answers with confidence. An on-device model that knows when it's wrong is worth more than one that's slightly more often right, because the first one composes with something bigger and the second one doesn't. Honest limits. 5. 1. It is not a general model, and I want that to be the thing you remember. Tool calling, device use, structured extraction, not conversation, not reasoning, not writing, not knowledge. Downloading this expecting a small assistant is a category error, and no amount of clever architecture changes what 45 million parameters can hold. 2. Tool selection accuracy on a large catalog is the open question. The retrieval head narrows to 5 candidates per turn, but how well it narrows, on a real catalog of 100 similar-sounding functions, is the number that decides whether this works in production. No published figure covers it, and it's the first thing I'd measure. 3. The benchmark claim is theirs, against a peer group they selected, and their own phrasing is trades wins rather than beats. That's honest of them. And it also means the results are mixed by their own account. 4. The 14 megabyte figure is the engine with weights baked in, which is a genuinely impressive claim, but the package fetches that engine from a model hub on first use. So the install experience involves a download. The offline path is documented, it just isn't automatic. 5. This is moving fast. A version shipped 13 hours before I read the page, commits landed 2 hours before, and the license changed from one permissive license to another 4 days ago. Read the current documentation and check the current license yourself, rather than trusting a video, including this one. Step back because there's a genuine shift underneath a small binary. For 3 years, every advance in this field has come from scale. More parameters, more data, more compute. And that produced extraordinary capability, alongside an assumption so widely held that it stopped being examined. That useful AI requires a big machine somewhere, either your own expensive card or somebody else's data center and a monthly bill. What projects like this one propose is that the assumption was never quite true. It was true for general capability, and we quietly extended it to everything. Because most of what people actually want from AI on a device is not general. Turn off the kitchen lights, add this to my calendar, pull the vendor, and total out of this receipt. Those are bounded problems with a small number of correct answers and a schema you can write down. They do not need a model that has read the internet. They need a model that reliably maps a sentence onto a function call, and it turns out that's a 45 million parameter problem, not a 45 billion parameter one, which gives the sentence to carry out of this. We have been solving small problems with large models because large models were what we had. The interesting engineering right now isn't only at the top of the scale. It's the work of figuring out how small a model can be and still be reliable at a job worth doing, and the answer keeps coming back smaller than anyone expected. 14 megabytes, 28 megabytes of memory, no network, on a wearable. That's not a scaled-down version of the future. For an enormous number of real products, that just is the future, and it fits on hardware that already exists in a billion pockets. So here's my question, and I'll pin it below. What's the smallest job you'd genuinely hand to a local model if it were reliable and free and never left your device? Not the impressive thing, the boring one you'd actually use every day. Parsing receipts? Controlling something in your house? Extracting fields from documents that shouldn't leave the building? Name the boring job, because I suspect the honest answers are far smaller and far more useful than the demos we all watch. And a list of them from people who build things is a better product roadmap than any keynote. Every link, the repository, the paper on the architecture, the engine project underneath it, the weights, and the install command is in the description. That's the standard here. The thing it can't do stated in the first 3 minutes rather than buried. The clever idea explained rather than admired. The benchmark phrasing quoted exactly as they wrote it because they chose it carefully, and no number claimed that I haven't read at its source. If you'd rather own your tools than rent them, subscribe. That's what we do every single day. I'll see you in the next one.